Hi, I am going to explain the answers to the Unit 1 free response practice test. Let me share my screen. Here we go. This is very similar level of difficulty, obviously not the exact same questions at all. But if you're wondering how long is the test, how is it going to be formatted, this is what it is. So here we go. Number 1 says write the complete, so that is not the noble gas formation, the complete noble gas or the complete ground state electron configuration for a Br minus ion. So Br is right here. Okay, so it's a pretty big atom. It's, all the way in the 4th energy shell down. So this is going to be a really long electron configuration. So we know that we start with 1s2, 2s2, 2p6, right? So I'm here now, 2p6. Then I'm at 3s2, 3p6, okay? And I've gone to 3p6 here. Then I'm at 4s2. And then you have to remember that this is 3d10, goes all the way over here. So 3d10. And then we're back to here, which is actually 4, right? Because the 3 goes down for the d orbital, but not for the p orbital. So then we're at 4p, and then normally bromine would be 1, 2, 3, 4, 5, but it's Br minus, which means there's an extra electron. So instead of 4p5, it's going to be 4p6. Okay. Number 2, write the noble gas configuration for PD3+. So PD is right here. So when you do the noble gas configuration, you look in this period and then you look one above it to figure out what the noble gas is that you're going to use. So that is krypton. So I'm going to put Kr in brackets, and that's everything before krypton is included. Okay. And then I know that this is going to be 1, 2, 3, 4, 5. So this is going to be 5s. 2. I'm just writing the whole thing right now, and then we'll take off the electrons just to not be confusing. And then this is going to be 4D, 1, 2, 3, 4, 5, 6, 7, 8. 4D8. Okay. However, this is PD3+. So if you wrote this would be incorrect. But you have to know that the two of the electrons, the first 2 electrons, are going to come off this 5s2. So if it was just PD2+, it would just be, this would be gone, and this would be the answer right here. But we have an extra electron, so the correct answer is going to be Kr. 5s2 is completely gone because 2 of those 3 electrons are taken away from there. And then it's going to be 4d7 because I took away 1 electron from the d orbital. So I'm going to erase that, scribble that out. This is the correct answer. Let's move on to 33. The composition of a sample of solid Rb containing a high percentage of the radioactive isotope Rb83 is given in the following table. Using the values in the table, calculate the average atomic mass of Rb. So what this is saying is that you can't use the number on the periodic table for Rb because this is not a representative sample. This is one that has a higher proportion of Rb that's radioactive in it. So this number 85.47 is irrelevant for this problem. Okay. So what we do with this is isotope 83 exists 33% of the time. 85, 50%, 87, 17%. This half-life, we don't care about. That's just bonus information. A lot of times on the AP test, there's extra bonus information that you just have to know to filter out. And so we just have to figure out what the average is amongst these. So we can kind of tell visually that the average is going to be a little bit lower than 85 because, we have the majority of our percentage is 83 to 85, but we have to figure out the exact one. So we're going to take the 83 isotope, which is, of course, the number of protons and neutrons. You be careful with that. Multiplied by 0.33 plus 85 multiplied by 0.5 plus 87 times 0.17. Okay, if you put that in the calculator, nobody wants me to watch me do that. That's really boring. It would be 84.68. And if you're wondering what the units are, it's AMU, which stands for atomic mass units. Letter B says, how many neutrons are there in the Rb87 isotope? So 87, this is the number of protons and neutrons together. Okay, that's what always the mass number is, right? That's how we represent isotopes. But if we want just the number of neutrons, we have to look at RB on the periodic table. RB always has 37 protons. That's what makes it RB. So we're going to take away 37. We're taking away the number of protons, and that's going to leave us with the number of neutrons. 87 minus 37 is 50 neutrons. Let's move on. Number 4, use the principles of atomic structure and Coulomb's law to explain each of the following. In each part, you must reference both substances. The atomic radius of lithium is larger than that of Be. So if we look at our periodic table here, okay, Li and Be are next to each other. So we know the answer is going to be about protons. They have the same number of shells, so that has nothing to do with it. So what we're going to want to say is lithium, Li, is larger because, and you're allowed to do these little abbreviations, BC is kind of commonly known as because, it has fewer protons, and I'm going to put the exact number, so it has 3 than Be, which has 4. Okay, so notice it says reference both substances, so I just did that, right? This means it has a lower, okay, right, because 3 is lower than 4. Oh, I ran out of space. I'll write real small. Nuclear charge. Leading to a lower force of attraction, right? Because it doesn't have as many protons pulling it in because those variables are proportional, making it larger, okay? Which has a lower nuclear charge and lower, sorry, it's getting a little cramped there, force of attraction, making it larger. You could potentially say like pulling on the electrons less, right? That might be a more complete way to answer that question. I think it's always harder to explain why something is bigger rather than smaller. It would probably be easier just to say Be has more protons, therefore it has a higher nuclear charge, pulling the electrons, more force of attraction, making it smaller. But it does ask us why lithium is larger. I think on the AP test, if you just explain beryllium as opposed to lithium, like in why Be is smaller, they probably would accept that as long as you include force of attraction and everything. But anyway, letter B says the second ionization energy of K is greater than the second ionization energy of Ca. So K and Ca are also next to each other. So this is going to be, this is actually not going to be about protons because we're looking at the second ionization energy. So that means how much energy it takes to take away 2 electrons. So if you think about K, it's really easy to take off this first electron. It doesn't even want it, right? It has a really low ionization energy. That's what it means, like really low, really easy to take it away. But as soon as you take away that electron, it starts to look like argon. And then it's going to be really difficult to take away that extra electron. Calcium has 2 valence electrons. It doesn't want either of them, right? Because once it loses both of them, then it looks like a noble gas and it's stable. So that's why it's going to be easier to take off both electrons from calcium than it is to take only 1 electron off from potassium, or 2 electrons off from potassium. So that's why the second ionization energy, right, taking away 2 electrons, shaky, is going to be more difficult for K. So how would we write that? So we would say K has 1 valence electron. So taking away a second would require a lot of energy since it will now look like a noble gas. Substances will take less energy to remove 2 electrons because both of those valence electrons. Okay. All right, let's move on. Following is the partial PES showing only the core electrons in bromine. So bromine's a really big atom, so its PES diagram would be really, really huge. So this is just the first electrons. It says circle the peak in the spectrum that corresponds to the 3s electrons of bromine. So all I have to do is label this. We always know the farthest to the left is the 1s2, 2s2, 2p6, and then we're at 3s2, and then we're at 3p6. Okay. So it just says to circle it, so I would circle it, and that's it. Get my point. Letter B, it says bromine and krypton both have 18 core electrons. So here they are. Okay. And that's just the core ones closer to the nucleus, right? Because they're both really big atoms, so they do have more electrons beyond that, but they both have 18. So their beginning PES graphs would both look the same. Would the peaks for the core electrons and PES for krypton be shifted to the right, to the left, or remain unchanged? So krypton, it has another proton. So it's a little bit stronger, right? It has more nuclear charge. So since it has that, it's going to be holding on to its electrons a little bit more closely, more strongly. And so it's going to take more energy to remove them, which is more binding energy. More binding energy is, remember, the axes are flipped, right? So if you have more binding energy, the peaks are going to be pushed to the left. So krypton's peaks will look exactly like this, except to the left a little bit because they're going to be more difficult to take off with that one extra proton. Okay, so we would say Kr has a higher nuclear charge. I can be specific, and I'll say 36, right? That's how many protons. Than bromine, which has 35. So it is it's like holding on to its electrons closer. So I'm going to say its electrons are strongly attracted to the nucleus, so more difficult to remove. Oops. So we'll have a higher binding energy, and its peaks will be shifted to the left, right? Because that's where the higher binding energy is, the left of bromines. Okay, just fit it in. So anyway, you'll have about 25 minutes to complete this test. I completed this video in 14 minutes. So you should be able to do it with 10 extra minutes, hopefully. And that is the level of difficulty. So hopefully that went well for you, and good luck studying.